Hi, everyone. My name is Ian Taylor. I manage the compiler team here at Google. And today we're here to welcome Chris Lattner from Apple. Chris is the lead developer, technical lead, et cetera, of LLVM, a free compiler originally from University of Illinois. He has a team at Apple working on this compiler. They've done a lot of very interesting technology, and he's here to talk about LLVM for us.
Great. Thanks, Ian. So, like Ian said, I'm here to talk about LLVM. Who here knows what LLVM is already? That's pretty good. Who here's actually downloaded and compiled it? Okay. So, I'm going to talk 2 slides of just high-level overview of what it is and what we do, right? So, LLVM is basically a compiler, right? Okay, so what does that mean? To date, we focused on 2 major things. We've focused on an optimizer and a code generator, components for LLVM, and a front end. And the optimizer and code generator is very similar to the GCC optimizer and code generator in some ways. It's SSA-based. The back end targets many different architectures. I think there's 10 major ones. The front end is based on GCC, and so it's GCC 4.0 front end. And the way that we compile code is that when the front end parses and converts the trees to GIMPL, we then take the GIMPL, turn it into LLVM IR. From that point, we use the LLVM optimizations and the LLVM code generator, and that's basically how it works. If you're to build a C compiler, that's a pretty good way to go. Some of the interesting things about LLVM is not really related to GCC. LLVM can be used for a lot of different things. LLVM is actually built with a library-based design, and so you can take the various libraries in LLVM, plug them into different things, apply them in interesting different ways. For example, LLVM supports link time optimization. It has since LLVM 1.0. And the way this works is basically the libraries for the optimizer get linked into the linker and get used at link time, and they operate on the LLVM IR, just like the standard compile time optimizer does. Another interesting thing about LLVM is that the code generator is actually pretty modular, and one of the features it supports is JIT compilation. And so LLVM doesn't require you to use JIT compilation, but it supports it. And so some of the early interest in LLVM has been because of JIT compilation, and so companies like Apple and Adobe have used this in some of the products that they're shipping. A lot of other companies use LLVM for other things. If you're interested, there's a web page that talks about it. The big feature of LLVM that people generally like is that it's really easy to understand, it's easy to use, it's well documented, and there's a good community built around it. And so if you have questions about it, you're using it for some interesting, new, crazy thing we didn't think about, there's constantly people asking questions. I have this idea, what do I do? What's the best way to implement this? And people are generally really happy to help out. Right? This is like a lot of open source communities, and LLVM, by the way, is open source. It's under a BSD license. And that's basically LLVM in a nutshell. So today my talk is going to be about 2 different things. One is the LLVM 2.0 release, which is the first .0 we've had since the first one. And after that, I'll talk about what we're currently working on and the stuff that's coming up. And I'll focus on 3 main things. I'll talk about LLVM 2.1, which is planned to be out in September. I'll talk about LLVM GCC 4.2, which is our front end ported to 4.2. And I'll talk about some new C front end work that's affectionately known as Clang right now. That's the code name. So, and if you have any questions, then feel free to stop me and ask me at any time. I'm happy to keep this very informal. So.
I just want to say one thing about questions. This will be going out on Google Video, so if you want to ask a question that's in any way Google confidential, please hold it till the end of the talk and talk to Chris afterward.
Yep. So first up, I want to talk about what's new in LLVM 2.0. And new is relative because 2.0 came out in May, right? So the major thing that LLVM 2.0 was focused on is implementing missing features, where missing means something that common software packages rely on the LLVM 1.9 and before didn't provide. And so, for example, there's a whole raft of ELF features like symbol visibility, thread local storage, symbol aliases, stuff like that that wasn't very important early on, but now that people are trying to build things like Qt or Mozilla, that suddenly becomes really important. It uses that all the time. Other features are target specific. For example, on x86, LLVM 2.0 brought full support for MMX. We already had SSC support and other things, but MMX is the unloved bastard child of vector extensions for x86, and code needs it, and we didn't support it. Now we do. It also brought PIC support for Linux, reg param parameters, things like this. There's a bunch of other miscellaneous things, for example, Pragma Pack, soft float support for targets without FPUs, precompiled header support, other features like that. These are basically, key features that GCC has supported for a long time. This is, fleshing out the feature set of LLVM to make sure that people can download and compile random stuff, right? And it works. Llvm 2.0 is the first release of LLVM that you can take something like Qt or Mozilla, build it out of the box, and it just works, right? Before you'd have to do little hacks to avoid regparam parameters or things like that. So now you don't have to do that. Looking forward, there's still some things that are missing in the missing features category. Chief among those is C++ exceptions. So this is currently work in progress. People in the open source community are very interested in this. For me personally, it's not a driving thing that I have to have, but I agree it's very important for completeness, and we'll probably have this with Llvm 2.1. The other big thing is long double. We don't support all the myriad of long double formats out there. This is also important. We will also add this. It'll probably be 2.1 or 2.2, something like that. Of course, being open source, if somebody comes and really has to have it and implement it themselves, it'll happen a lot sooner, right? There's also a couple other miscellaneous things like built-in apply and nested, taking the address of a nested function. Again, when people want that, we implement it, but there isn't high demand. So besides implementing just missing features, there's also some other useful user-visible improvements in Llvm 2.0. Particularly, the optimizer is significantly better than 1.9. So we have rematerialization support, simple rematerialization support in the register allocator. We have the ability to promote unions into registers. So if you take a vector and you have a union with a vector and an array of floats in it, you store into those floats and use the vector. Well, now that will become a p-insert in W instruction in SSE, for example. There's better switch statement lowering, there's better register pressure, minimization algorithms, stuff like that. In addition to just better code, there's also a few other miscellaneous things. So compile time's better. We now can turn LLVM intermediate representation to MSIL, something that everybody's always wanted. And the Ada community is actually very interested in LLVM, and they've been contributing support for the lesser-known GCC tree features that we didn't support as well. And so Ada with LLVM actually works pretty well with 2.0, as long as you don't take the address of a nested Ada function, because that would die. So because this is a more technical audience, I didn't just want to blast you guys with features, because that's not what's interesting. I want to talk about some of the specific things that we changed in Llvm 2.0 that are interesting from the compiler design standpoint. And so the one interesting aspect of LLVM is that the IR has two main forms. It has two main on-disk forms. It has the human-readable text format, which means that you can hack out LLVM IR in VI. It also has a compressed binary format, which is very useful when your link time optimizer is talking to your compiler, things like that, right? And so up until 2.0, we've always maintained backwards compatibility of these files. And so if you had an LLVM 1.3.ll file, for example, LLVM 1.9 would read it. Well, since we had this nice 2.0 number, we could justify dumping that backwards compatibility, auto-upgrading support, and make some more interesting changes we want to make for a long time. So I want to talk about two of these, one of which is signless types and one of which is arbitrary precision integers. So in LLVM 1.9, the type system in LLVM is very similar to C or GIMPL. If you have an integer type, it turns out that we would just represent it as a signed int or an unsigned int or a signed long or an unsigned long. Something that has a fixed size, but the signedness is encoded explicitly into the type. In LLVM 2.0, the change is to get rid of the sign from the type and change the operations themselves to be signed. And so somewhat like RTL, you suddenly now have 16-bit integers, 64-bit integers, and you have sdiv udiv instead of just divide, which changes behavior based on the type, right? So why do we do this? There's a couple of reasons. One is that the IR itself is smaller, right? So now we don't have to have casts that convert from int to unsigned int, right? Not having int unsigned int casts make people optimizers happier because they don't look for two instructions that are supposed to be back-to-back, but oops, there's a cast in between them, and that disables the transformation, things like that, right? It also makes it smaller if you care about the memory footprint of your compiler, about link time optimization, things like that. The other good thing about this is that it makes the operations themselves more explicit. A great example that was hated before, at least by me, was cast. So cast in C can mean a whole bunch of different logical operations depending on the source and destination types. So if it's an integer to integer cast and the source is signed, well, that's a sign extension, right? Well, if it's a integer to float and the source is signed, then that's a sign, whatever. There's actually 10 or 12 different logical operations. And the nice thing about this change is it makes that all explicit. So you have a sign extend instruction. It's very easy to analyze and transform. The other bigger driver is that it exposes it more closely matches what actually is happening in the program. And so I'm going to give you a contrived example, but this does actually happen when you start talking about induction variable analysis and insertion and elimination. So this is a simple example where you have basically an integer coming in, you convert it to a signed integer, you do 2 adds, you add 4 to both of those, you cast it back to sign, you do subtraction. Okay? And so in Llvm 1.9, the IR is basically the identical thing to what you get in C, right? You have a cast that changes the signedness, you have a couple of adds, you have another cast, and subtract, right? This is a very literal translation. This is very similar to what GIMP would give you. Right? Incidentally, this is what the Llvm textual representation looks like. It's basically SSA, machine code looking operations. So when we went to 2.0, of course, these casts, which just changed sign, go away. Instead of int and unsigned int, now we have just a 32-bit integer, right? And so the casts go away. The bigger impact of this, though, is that now suddenly these adds are obviously redundant, right? Before you had adding A and B where they had adds with different type. Well, you can teach your redundancy elimination stuff to handle that, but really you want to just say, is it doing the same operation? And the problem is that these 2 instructions did the same operation, but they looked different to the optimizer because the types were different. And the type didn't matter for this operation at all. If it were a divide, that would be a different thing, right? And so with this, the optimizer can trivially delete one of these, then it decides this is a subtract of x from itself. That's 0, well, so the whole function returns 0, right? This is just, again, a contrived example that shows why getting sign out of the IR was a good thing for us. And you don't lose anything from an analysis perspective. So the other thing this let us do is extend the type system to allow arbitrary precision integers. And so in Llvm 2.0 and beyond, you can now declare your favorite 123-bit integer, right? And so you can do operations on these weird, long, or really short integer types. And the optimizer fully respects that. All the transformations are updated to do the right thing with them. This work was driven by the EDA industry and the people doing hardware synthesis from Llvm IR. So for them, the reason they wanted this is that, well, a 13-bit multiplier is significantly cheaper than a 16-bit multiplier, or being able to squeeze 32-bit divide down to 24 bits is a big deal for them, right? For most people, the big win for this was 128-bit integers on 64-bit platforms, and the Llvm transformations and things support any type on any system now, which is very nice. From the implementation standpoint, doing this was a real pain because up until now we had all these bit twiddling optimizations and other things. They all used a UN64T, which was definitely big enough to represent all the interesting integer values, right? Well, that's not true anymore, and so now we have this APInt class which abstracts that. It's extremely efficient if your types are 64 bits or below. If it's above that, then it handles them gracefully but not efficiently. But this actually ended up making the code a lot cleaner because now you didn't have to handle the idea of I'm doing 8-bit integer arithmetic within a 64-bit container, for example. You just declare it as an 8-bit value and it does the right thing. Yeah?
Does the code generator do sensible things if you give it an I1024 when you usually do the Llvm?
So the code generator currently...
Can you repeat the question?
Yeah, the question was, does the code generator do the right thing if you give it a 1024-bit integer? And the answer is no, it does not do sensible things right now. It could be extended to do that. We support arbitrary width vectors in the same way. So if you declare a 128-element vector of floats, we do correctly turn into 4-element float operations on SSE, for example. And so you could do the similar kinds of things. So until now, the front end, the optimizer support these. The code generator has marginal support, but not wonderful. So that's basically all I really wanted to talk to you about with Llvm 2.0. If you have more specific questions, I'm happy to answer them. But a lot of the interesting stuff is happening in the future, and That was May. May is so long ago. I mean, who keeps track of any of that stuff, right? So the three things I wanted to talk about were Llvm 2.1, which is our next release, Llvm GCC 4.2, which is upgrading Llvm GCC to 4.2, strangely enough, and a new C front end that we're working on, which I mentioned before. So Llvm 2.1 is slated to come out in September. One of the interesting things about the Llvm project is that we crank out releases every 3 to 6 months, and this has a number of advantages for us. We don't have to worry about sub-dot releases, because if we just release something and your feature doesn't make it in, a new release will be coming out really soon anyway, so it's not a big deal. The hard part about this is getting developers to understand and cope with this, and we do this 2 ways mainly. Incremental development is a really hard thing for some people, but it's really important. This lets us do development on mainline instead of on development branches, which means that people are constantly testing work being developed by other people on different projects, and we don't have these periods of instability where huge changes slam back into the mainline tree, for example. So the end result of this is that even though Llvm 2.0 came out in May, in September we'll have a new release out, and we just keep pumping them out. So one disadvantage of this is that each release has correspondingly fewer features because it's a shorter time span, but Llvm 2.1 will probably include dwarf zero-cost exceptions for C++, some more improvements for the optimizer, and significantly some big speedups for the optimizer. In particular, the 2 optimizations related to dead store elimination and load transformations are being revamped, and they used to take 40% of compile time in certain cases, and now they'll take next to no time. So this will make users happier. So if you're all hacking on Llvm today, you have plenty of time to get your changes in and ready for the next release. So the second big project underway within the Llvm community is upgrading Llvm GCC to 4.2. And so this is the obvious merge process of taking Llvm GCC 4.0, which is based on the Apple 4.0 GCC tree, and upgrading it to the Apple 4.2 GCC tree. And we use the Apple tree instead of the FSF tree just because it has more features and has more stuff, and a lot of Apple people are working on it. The most significant interesting things about 4.2 for us, because we're not using the optimizer, we're not using the code generator, remember, from GCC, are front-end features like OpenMP, the new Fortran front-end, the ADA improvements, which have actually happened. The ADA and Fortran communities in Llvm are very, very, very happy about 4.2 and can't wait for us to get there. Other features of the new recursive descent parser for C. Again, since we skipped 4.1, there's a bunch of new features in there. So this work just started like a month ago. The status is that it was merged in, the compiler builds, all the Llvm stuff seems to work in terms of it's hooked up right. So now it's a matter of churning through the bugs, finding out that constructor changed, semantics from 4.0 to 4.2 and updating that, and working through all the bugs and getting it to work. So if I had to guess, I would guess that this will be ready by 2.2 timeframe, so which will be 3 months after September, so say December or January, something like that. Of course, it goes faster with help. So the third piece is the more is what I've been working on most in the last couple months, and it's a new front end for Llvm. And so this is a new front end. It's been released open source recently. It's under the Llvm BSD license. So it's a new front end for C for Llvm. So the big question, of course, is why would you bother to do this, right? We already have Llvm GCC. Llvm GCC is great. Supports C, C++, Objective-C, ADA, Fortran, Java, all this stuff, right? Why are we doing this? Well, the answer has multiple different components, right? One component is that at Apple, we really care about IDEs. And unfortunately, GCC does a really bad job at servicing the IDE. GCC does a good job at compilation. It does a really bad job at parsing code really fast and finding all the definitions and uses of variables. So when I double click on something, it jumps to the correct definition in the correct scope, right? This is kind of like the Doxygen style of analysis, right? Well, the hard part about this is that you want to do it extremely fast because you want it to be up to date as the user's typing in their window, right? GCC is just architecturally not built to support this kind of use. Another thing is that GCC is really not set up to export an AST, so the clients like source analysis tools can take that AST, grind on it a little bit, and then output some interesting information about it. There's been work to do that in the GCC community, but it doesn't seem to have taken off very well, and there's other problems with that. The second major reason is that GCC just doesn't preserve enough information. In particular, we're interested in full column number information. GCC has two different ways of representing locations, and neither of them actually preserve all column number information. They both saturate if you go too far to the right, for example. They dynamically adjust, so it's unlikely to happen, but it's still a problem. The other more significant problem is that as it parses, GCC passes everything through fold, right? And fold does all kinds of interesting, useful, wonderful simplifications, but the AST, the trees that you get out, don't look anything like the source code at the end, necessarily. And you can't disable this either, because if you do that, then the parser dies in mysterious, strange ways, because it assumes that basic things are getting folded, which is extremely frustrating. And so if you're writing something that wants to look for all uses of X, and the source code contains X minus X, and you go in your refactoring tool to rename X, and it misses the X minus X that occurs somewhere, the user's program won't build, right? That's a real big problem. And coupled with the fact that if you're trying to rename X and you can't find it because it's in a weird column, that's another big problem. Right? So another point that's more easy to argue about, it's less empirical, is that the GCC front end is difficult to work with. And this is a personal opinion, but I've heard this a lot from people. There's two major problems. One is that if you're new to GCC, the time to ramp up is horrible. It's very painful. GCC is a very complicated, interconnected system, and getting up to speed requires understanding a lot of it, right? You can't just learn a small piece of it. To me, that's a huge problem. The second issue, which is becoming less of an issue as time goes on, is that there's a lot of politics around GCC. For example, LTO wasn't allowed to happen for a very long time. Again, that's changing. But a combination of politics and the implementation being really hairy make it really difficult to make any meaningful change. So for example, switching GCC to use signless integers or arbitrary precision integers is pretty much impossible. I'm not saying it is impossible, but it's certainly very, very difficult, right? That's not something you can do in a single release cycle, with a series of incremental changes. And finally, another big issue is that GCC is very slow and it's very memory hungry. And I'll talk about this a little bit more in a few slides. The combination of these things say that we want to reevaluate the way front ends work, the way front ends interact with the optimizer in the back end part of a compiler, and see if we can do something better. So looking forward, our goals for this are then not to solve all of world hunger and all the world's problems and change the way that everything works. We have very specific concrete goals. One is that we want a unified parser for C, C++, and Objective-C. The GCC parsers are split between C and C++, which means that a language extension like Objective-C needs to be implemented in both places, right? If you have a unified parser, besides sharing some amount of logic and making each one a little bit slower, perhaps, it makes it so it's more difficult to extend both with a single extension. The other feature is that we want to have good diagnostics coming out of the front end. A front end of a compiler has two main features. Well, assuming the compiler compiles your code correctly, there are two areas where a front end can contribute to the end user. It can either be fast, or it can produce good diagnostics, or hopefully both, right? But aside from that, all you want from it is to do the right thing. I guess it can also support all the features you want, which is also important. But these are our focus. And another important feature of this is that we want to have GCC compatibility, because there's a bazillion lines of C++ and C. There's a ton of C code out there in the world, and we want to be able to support it, which includes all the nasty, gnarly extensions and weirdness. So we plan to build this the same way that we've built the rest of LLVM. We have a library-based design where we have cleanly broken up the various pieces of the front end. So we have Lexer preprocessor parts, parser parts. We have semantic analysis parts. We have converters that convert from ASTs to LLVM. They're all separate libraries, for example. What's that? Okay. So the good thing about libraries, among other things, are that it's very easy to dive in, understand them, and move on, because you don't have to understand the whole system, right? So again, we want to be multi-purpose here, and this is talking to you before. In an IDE, you have multiple different clients. You want to be able to support them all well. That's a primary goal of ours. And of course, we want it to be fast, right? And so this both includes compiling code fast, having a low memory footprint, but also allowing interesting optimizations like caching, lazy evaluation, supporting multi-threading within the compiler, things like this, which are very difficult to retrofit into an existing compiler that wasn't built to support those. So with all those goals, obviously, there must be something we're not trying to do, right? So non-goals are that we're not trying to support anything except for C family languages. And so we are building new ASTs, but we're not going to try to shoehorn Java into using our ASTs, right? If you want to build a Java front end, a Java front end for LVM, that'd be fine, that'd be great, but build your own ASTs. They're not the same. Java and C look the same, perhaps, but they're totally different languages. Likewise with Ada or Fortran, completely different languages. We already have an intermediate representation that's good for analyzing and optimizing code, the main LVM IR. There's no reason for this front end to do the job of some other front end's ASTs. Another non-goal is that we're not trying to or planning to obsolete GCC. One of the common criticisms I hear is that we're trying to kill GCC, which of course is completely wrong, right? GCC has a lot of strengths that LLVM can't touch, right? There's a lot of things GCC will always be able to do that LLVM will never be able to do because it's not in our interest. It's not what we're trying to do. LLVM and GCC are two different projects which have some amount of overlap, and people tend to focus on the overlap. But they're inherently different projects with different communities trying to do different things. And so we're not trying to obsolete GCC, and that's not a goal. We're trying to solve problems. So anyways, on with the actual concrete details. This already exists. You can download it out of Subversion. So when you run on the command line, it looks just like a compiler. We have GCC compatible options for the most part. It's written in C++, so like the rest of LLVM. It's written in a tasteful subset of C++. And so we don't do all the wild, crazy stuff that you can do. People have commented often that our code is not as horrible as people expect C++ code to be. So if you're afraid of that, check it out, take a look at the code. So when you run it, it looks just like a compiler. As I mentioned before, we have full column information, and so if you have a problem, we can give you a caret diagnostic, right? This is similar to a lot of other compilers out there, where it prints the line of code and it prints the location on the line of the problem. In addition to just being able to analyze code, we also have a bunch of options for performance measurement. So for example, one of the features of the front end is that it's architected as libraries. There's two different libraries for parsing and for semantic analysis. What this means is that you can parse code without building an AST at all. And so this parse no-op option says, parse the code, don't build an AST, don't do any of the semantic analysis stuff. Well, rather do as the minimal amount of semantic analysis, which is basically keeping track of type defs and their scope. And you don't have to build an AST, just parse, right? Well, the interesting thing about this is that if you can separate those two, you can actually measure how much time you spend parsing versus how much time you spend building an AST and doing the type checking stuff, right? So we have a number of options, pre-process, but don't print the output, because what I'm trying to measure is how much disk I/O am I doing, how much macro expansion am I doing, stuff like that. Another nice feature is that we have a pretty printer that actually generates, for the most part, legal C code. And so if you give it a C file, it will give you the macro expanded C AST that comes out of it. And so it's just, what's that?
Is that the dump compilable?
Yeah, this is compilable. So I mean, the C file looks the same probably, but actually the input C file had some macros that got expanded. I didn't show that, but you could compile that. So, is that the question?
Yeah.
The question was is the output compilable, I guess. So there's another feature. So for our diagnostics test suite, we don't build all kinds of stuff into the tickle. Our tickle code is very, very simple. It just says run this program. And the checker for whether or not diagnostics are emitted on the right lines and stuff are actually built in the tool itself. And so if you run with this parse AST check, for example, or run the parse parse, build an AST, and then check that the diagnostics emitted are correct. And so on this test case where this is not legal C code, if I say, aha, I want an error that's some weird string, and I run the checker on it, it will say, aha, on line 1, you expected this, but it didn't happen. You didn't expect this, but this did happen. And so you got an expected identifier error, right? And so one of the cute things about this is that because it's built with all the same infrastructure as the rest of the compiler, this expected error annotation actually occurs after an escape new line. And that's fine because it's using the Lexer. The Lexer knows about escape new lines. It knows about trigraphs. It knows about all that horrible stuff. And so that kind of thing continues to work. Right? It also meant that we didn't have to build yet another thing that scanned through C code. Right? I mentioned diagnostics before. One of the nice things about this is that it gives you good diagnostics. Here's, again, a simple example. Here's some code. It has a struct. It has a couple functions, and 2 lines of code in this function body. When you compile this with GCC, you get 2 errors. They say there's an invalid type argument to unary star. That's true, and it's talking about this sum a.x. But given this error message, I have no idea what it's talking about or why that's invalid. I just know it is invalid. The second thing is it says I have invalid operations of binary plus, right? Again, I have no idea why they're invalid. I have no idea which binary plus it's talking about, right? If you run this through Clang, so here I took away the source code, so you don't even have to see the source code, and these are the diagnostics you get out. It doesn't give you color-coded diagnostics, but it could, and in an IDE it could draw nice little boxes or whatever, right? But here it says, at that unary star with the sub-expression, your indirection requires a pointer operand, right? It's not that it's invalid for an arbitrary reason. It requires a pointer. Give me a pointer. That's the problem, right? And it says that it is an int. So now we know exactly what's wrong. We can fix that. Here again, the second line, it tells us exactly which plus it is, and especially when you get nested, complicated stuff coming out of macros, it's really useful to have an indication of what sub-expressions it's talking about, particularly if they get heavily parenthesized, right? And so it actually tells you exactly which sub-expressions, and it does the right thing there. And it says that it gives you the 2 types, right? Now, giving types in diagnostics is something that is relatively easy to do, right? GCC does this sometimes for certain things. It doesn't happen to do these, but it doesn't give it for others. The problem, though, is that types can be arbitrarily complicated, right? And so I'm sure everybody who's done C++ programming has seen the compiler spit out, you got a basic string of tar traits of this, of that, and the other, whatever, right? This is basically because GCC does an incomplete job of tracking type def information. By the time it goes to give a diagnostic, it has lost the fact that you're using a type def. And so we don't support C++ well enough to handle basic string of char yet. But this does occur in C also. And we do actually retain type def information well. We propagate it through the AST. We efficiently can compare types and do all that kind of stuff. So this is something we think is really important, especially having to suffer with writing C++ programs for many years, right? There's other minor features. So for example, each diagnostic has a unique ID, so you can control them on a per instance basis. You can group them, things like that. The location tracking is actually better than column information because if a token came from macro expansion, we both know where the macro expansion is and where the token came from, for example. And so we actually track that information, which requires more bookkeeping, but it's very important for certain clients like refactoring. If you want to refactor code, knowing that something came from a macro expansion is really important, right? Because you need to throttle back what you're doing or handle it. Okay. So are there any questions so far? So where are we, right? So this is still very early work. You're not going to download this and build a Linux distro with it. Again, it's broken up into a series of libraries, and so the Lexer and preprocessor are already well done. We have one of the people who co-developed the GCC preprocessor scrutinizing everything, and he's convinced that it's doing the right thing in all of his crazy test cases. The C parser is about 95% complete, which is good. I think C99, so, and the GNU extensions as well. The major thing we're missing is for GNU style inline ASM, for example, we don't build an AST node for it. We just parse it and keep going. Minor things like that. Semantic analysis is not so well complete. I'd say it's about 80% complete. So this includes omitting all the errors when you have type mismatches and stuff like that. We're continuing to work on this. This is basically largely going through the spec and making sure you implement it all well. The nice thing about this is that there is a spec, well, except for the extensions, but there is a spec, and so you can be sure that you're doing the right thing and you're implementing it correctly. The harder part are warnings, right? Warnings require a lot more fuzzy kind of, I'm trying to help the user even though the code's not invalid, but it's really questionable, right? And so that's something that we're not nearly as far along with. We recognize that it's important, but we haven't had much emphasis put on it yet. Also, code generation is very early on. You can do a lot of arithmetic. You can do scalars, vectors, arrays, loops. You can't do crazy things like structs. I mean, really, who uses those? Yeah, they should use scalars. So we're obviously continuing to work on this, but as we do this, we're continuing to say, what can we do and how are we doing on those pieces, right? And so how do we evaluate ourselves? What interesting things can we apply this to? And so one easy thing to do is compile time performance, right? Because compile time performance is something that's very important to us and it's easy to quantify. So to me, at least, there are three interesting areas where you'd want to look at compile time performance, and these are kind of ranked in order of hardness, I guess. When you're building a release build, so I want to do performance analysis, I want to ship it to a customer, I want to give it to my internal users so they can live on it, whatever. You're doing a release build where you turn on all your optimizations. If you're working on a piece of code, you're sitting in the editor doing compile, debug, edit, compile, debug, edit, compile, debug, edit, compile, debug, edit, over and over and over and over again, right? If you have a source analysis tool, so for example, you're doing indexing where you're trying to find definitions of uses of some variable, the user types some code and then double clicks, or whatever the action is, on X, you want to jump to the right X immediately, even though they haven't even hit save yet, right? Well, this means that you have to be parsing it incrementally, extremely fast. The time constraints are really, really hard because the user's editing their code and you're supposed to be parsing it. It might not even be valid, right? So of these three cases, the front end is really only interesting in two of those, right? In the first case, all the time spent in the optimizer, it's spent in the code generator, spent in the system tools like that. So the front end doesn't have a big impact on that. In the development build, obviously the front end is critical because you're compiling for at least 1/3 of those cycles, right? And for the source analysis tool, it's even more so. And so I'm going to start talking about these two here. So the question is that if you want to optimize your front end, where is it spending its time? What is the problem, right? So if you look at a typical application on a Mac, and a Mac is particularly bad, but this happens on every platform to some degree, particularly when you're using libraries. What we end up seeing is that the application consists of a core of a couple dozen or a couple hundred source files. These files are marginally big. There may be a couple thousand lines of code, maybe 10,000 lines of code. Wow, But so the code that makes up the application isn't that big. The problem is that they include a lot of libraries, and these libraries have these gigantic headers. On the Mac, in particular, developers are encouraged to include the umbrella header for the subsystem they're using. So, for example, Carbon is the C interface to the Mac GUI API stuff, and it includes a whole bunch of sub-header files. Cocoa is the Objective-C version of this. Same thing. It's an umbrella header that includes a whole bunch of other headers, right? If you're using an XML parser or embedded web browser thing, you'll likely have similar things, right? And so the problem, of course, is that headers are huge. If you take your 10,000 line program that pound includes carbon.h, your 10,000 lines of code are a pittance compared to the amount of code the compiler has to deal with. Carbon.h, for example, pulls in 558 different header files, all of which have to be looked up on the file system through multiple include paths, which probably have dozens of entries on them because they probably have dozens of entries on them. The text for the headers alone are 12.3 megabytes. 12.3 megabytes just for the headers, right? And out of this, you get thousands of function declarations, enums, you get tons of type defs, you get all these macros, all the stuff that gets pulled in, and then they have their 4 functions or whatever, and the compiler's done, right? And so compile time, when you're looking at least the debug, execute, compile, turnaround cycle, is largely dominated by the parser because the parser has to type check, analyze, look at all of this code, right? If there's an error in a system header, the compiler is required to tell you about it, right? Even though there's probably not, but if you did some crazy -d, int to something else, you're going to get lots of errors, and the compiler is compelled to tell you about that. So it actually has to look at and analyze the entire header, all of its contents. The optimizer, on the other hand, has really got it easy because after the front end runs, it says, okay, here's the 4 functions and maybe an inline function from the header you have to compile. Go for it. Well, it grinds on those and it's done, right? The front end has very different time-space trade-offs and other constraints here. And so if you look at this header, like I said before, it's about 12 megs of input source. After you run through the preprocessed source is only 3.5 megs, right? And so people have observed that lexers and preprocessors are very performance sensitive, right? And this is exactly why. The preprocessor is confronted with, in this case, 4 times as much information as the parser, right? The parser and the lexer piece only has to deal with, 3.5 megs. So when we look at the memory usage of our ASTs compared to these, it's actually pretty good. This breaks down our ASTs by a couple of different flavors. So we have the actual identifier hash table, for example. We have declarations, identifiers and characters, and statements and expressions. And because it's a header file, there aren't a lot of statements and expressions, right? Because those are only in inline functions. This is mostly enums, mostly in function definitions, stuff like that. And so this explains why decals are significantly more than statements or expressions in this case. And headers are generally like that, right? If you compare this, so one of the interesting things we found is that we're actually pretty good for space because even though our ASTs contain fully instantiated type def information, completely track source location information for any for any binary plus, we know exactly where the extents of the left-hand sides and the right-hand sides, which is required to emit these nice diagnostics. Even though we're tracking a lot of information, our ASTs are only about 30% larger than the preprocessed source, which we think is very good. Of course, if for the people who work on GCC, you can guess that GCC trees don't fare nearly so well. GCC's the historical design of it's actually kind of bad for this case, and this is one of the worst cases for GCC, because specifically GCC puts a lot of back-end information into the trees, right? You have RTL fields, you have alignment fields, you have all the stuff that really only the code generator looks at. You have decal, assembler, string, all the stuff, right? Well, this is a header file. The header file isn't using any of this stuff, or is using a tiny proportion of this stuff, because most of the stuff never makes it through the code generator, right? And so all of this stuff and space and all this extra data is just wasted, right? It's just zeros in your address space. And this is one reason why it's really hard to use GCC for a refactoring tool, for example, right? Refactoring needs to have a global view of your entire program, all of the declarations, all of everything at once, to be able to find out if I rename X, where do I need to update it, right? Things like that. And the memory use is a big problem. So another interesting experiment is compile time, right? That's a natural thing. Because we can separate the semantic analysis from the parsing itself, we can actually measure preprocessing, parsing, and the semantic analysis, AST building pieces in isolation. And so we found that preprocessing, unsurprisingly, is the biggest chunk of our time spent on carbon.h, of 0.16 seconds. The parser is actually really, really fast because the parser is completely trivial, right? I mean, the parser is basically taking tokens out of the preprocessor and changing state. It's not really doing that much, and the time it spends is proportional to the number of tokens that come out of these headers, not proportional to the number of macro expansions or the 12 megabytes of source code that come in or anything like that. So the parser is actually really fast and really simple. The semantic analyzer, on the other hand, has a different place where it spends all of its time, and that's actually building these ASTs. And so allocating all this memory for the ASTs is expensive, takes time. Doing the type check is expensive and takes time, of course, relative to the parser. The parser is very simple, and it runs basically within cache, except for the preprocessor. Right? Ian?
C code or C++?
This is C code. So we've also looked at some Objective-C code, but since we're doing semantic analysis, that would require semantic analyzing C++. Our C++ support is minimal. We support bool, static cast, a couple of really trivial things, but not nearly enough to be able to do anything interesting, and not nearly enough to get interesting performance metrics. So, yeah.
So where is the time to look up the 558 files?
So the time to analyze, find, do all file system stuff for 558 files is all included in the preprocessor. And so the preprocessor has to scan the file system. It has to do, it has to lex, scan the file system, handle macro expansions, do all of that stuff. So the preprocessor is the nasty, performance-sensitive piece. So if you look at the percentage breakdown, right, we're spending 35% of our time in the AST building, type checking stuff, and 65% of our time in preprocessing. Again, this is for a massive header file, right? If you have 12 megabytes of source code that actually contains statements and declarations and expressions and other stuff, I'm sure it would be weighted more towards the semantic analyzer. Right? If you look at GCC4, and here this is Apple GCC4 because it's what I happen to have available, GCC4 actually has very similar performance characteristics in that it spends a whole lot of time preprocessing. And so the preprocessor is about twice as slow as the Clang preprocessor. But again, GCC builds all of these trees. All these trees take a lot of time to allocate, manipulate, transform, analyze, type check, all that stuff. And so partially because the trees are bigger, GCC is slower. GCC also has questionable algorithmic decisions, but I won't talk about that very much. Yeah?
So, semantic analysis you are doing about fact checking, right? So, in fact, how easy it is to add a new type qualifier?
So the question is, how easy is it to add a new type qualifier? It's actually pretty easy. The nice thing about it is, and one of our goals is that if you know C or you know C++ or you know the language that you're trying to deal with, the ASTs are very obvious. So we have, for example, type qualifiers. We have an integer type. We have unions and structs as first-class things in the type, in the class hierarchy for the ASTs. We have all of the things that map directly to C because we're not trying to be a unified AST for all languages. And so basically, to add a new type qualifier or add a new thing, you basically find the pieces that are handling the existing type qualifiers, add yours, update the things, look at those, and it's pretty straightforward. And yeah, you can change the rules. You can do whatever you want. I mean, the source code's there, right? So the problem with that is that there are a lot of rules that have interrelated pieces. And we do have good predicates for what is an integer constant expression, for example. If you want to change the definition of what an integer constant expression is, you do it in one place. Things like that. So I'll keep going. So if you look at the numbers, we're about 2.5 times faster than GCC on this one test case. And again, it's a big header. It's a very important for certain people case, but it's definitely the worst case for GCC. And the problem is that for us, the worst case for GCC is impacting our customers on a daily basis, right? So it's somewhat contrived, but it's real, and it's impacting customers. So while 2.5 times is good, we actually want to have significantly more than this. And I have no numbers to back up 10x, but I believe you can do significantly better than this. And the observation is that this isn't using, so we're not using precompiled headers, we're not using any tricks, right? When you start using tricks like precompiled headers, when you start caching aggressively, using multi-threading, other things, I think you can get significantly better speedups. One of the things we're interested in, again, is an IDE. And in the context of an IDE, by the time you've compiled your whole program and are about to run it, well, your IDE should know everything there is to know about your program, so that when you go to click on refactor, it has all the information it needs, right? And so a combination of being intelligent caching, doing things in the background, all of this stuff can contribute to an experience that feels a lot better. And following that, once you have these ASTs, you can do a lot of interesting things, right? Clicking on X and going to its definition is one example. Another is, source code refactoring. If you have persistent ASTs, you don't need debug information because the debug information captures just a tiny subset of what the ASTs do. One of the things we're very good with in the Llvm community is knowing how to serialize IR. And AST is just a tree-ish IR, where Llvm IR is more of a linear IR, but it's the same kind of idea, right? And so if you can make it efficient to access and process lazily, then you can do great things. So this is all wonderful if you're sitting on your desktop machine building stuff. The question is what about parallel builds? And I mentioned before that if you're building at 04, right, the front end doesn't really matter. Well, that's not entirely true, right? Because if you're at some place that has gigantic clusters of machines, you might be trying to distribute your builds across all these machines. And so to do this, one popular tool is a tool called diskcc. The way diskcc works is it's actually architected to drop into your makefile. So you drop in, you use cc equals diskcc, and instead of invoking gcc, your makefiles invoke diskcc. And you say make-j 147, and you get a lot of things happening in parallel, right? Well, so the way diskcc works is that it actually preprocesses all of your source on the local machine, sends the .i file across to the slaves, which then optimize and compile it, right? So this is imperative if you don't own the file system, you don't have a unified file system, because to get the same binary out at the end, you need matching system headers, application headers, library headers, all of these things, and getting those all in sync is very difficult. By preprocessing before you send it across, you solve that completely, and you just have to worry about having the same version of your tools, which is easier to control because those can be installed locally. The problem, though, is that your preprocessor becomes a significant scalability problem. This is a quote from a paper written by Martin Poole, the diskcc guy, and he says that diskcc tends to stop scaling at 10 to 20 processors, depending on the flavor of your code. Now, if you're dealing with Apple code where you have ridiculously huge headers, it doesn't scale nearly this well, right? Because you're doing all your preprocessing on your single machine, and so if your single machine can only preprocess, four times as fast as the back-end machines can compile, well, you're limited heavily by that. So the question then is, what can you do if you have huge clusters of machines lying around, right? Well, the GCC community, and Google certainly has helped with this, has actually looked at optimizing GCC's preprocessor, right? And so I was discussing this with somebody before, and they said, oh, well, GCC 4.0 sucks, and especially Apple GCC, because it has all kinds of nasty, horrible stuff in it, and GCC 4.2 is much better, right? So, and in fact, he's right? GCC 4.2 is significantly better than GCC 4.0. And what I measured here is I took the 4 biggest benchmarks at Spec CPU 2006, just because they're well-known, they're available, people can get them, and took the biggest in terms of the preprocessed output. And so if you look at Xilinx BMK, for example, to compile this sucker, you have to end up processing 291 megs of source code, a lot of which comes from headers, right? And it's this big C++ app. Likewise, DL2 includes big pieces of boost and things like that, right? And so if you look at this, the speed up that you get from going to GCC 4.2 versus the Apple 4.0 is about 6.9%, which is pretty good, right? That means you scale 6.9% better. So before I claimed, of course, that our preprocessor is significantly faster. So if you compare 4.2 to our preprocessor, which again is very conformant, and you can use it independently of the parser, which isn't done yet, and the preprocessor is, we actually are significantly faster, right? Across these programs, for example, you get between a 58% speed up and a 48% speed up. What that means is that you can diskcc and distribute your work to twice as many machines, right? Your scalability is twice as good. And so across these 4 machines, you get an average speed up of 58%. This is just for changing the diskcc step that invokes the preprocessor to invoke the Clang preprocessor instead of the GCC preprocessor. No other changes, right? You're still farming it out, compiling with GCC. You're not using LLVM at all, other than the preprocessing stage, right? And suddenly you scale twice as well, which is pretty powerful, right? That's a very useful deliverable thing that our users can benefit from. But again, the point of this framework isn't, question?
If you preprocess it locally and then distribute it, don't you lose all this nice meta information about where each character came from, where the expressions are out of macro expressions?
So the question is if you preprocess locally and then move it remotely, don't you lose all the information about where the tokens came from and stuff like that? So the answer is yes, you do lose information about macro expansions, but pound line markers do tell you the line number, and within the line, assuming there's no macro expansions, the column numbers are retained, so you're fine in that respect, or they're mostly retained. In practice, GCC doesn't do anything with column numbers, well, except that's an exaggeration. In practice, GCC generally doesn't really do anything with column numbers, and as long as you have pound line markers, you'll get good debug information. And so If your backend is compiling with GCC, it doesn't matter. So DistCC is only really interesting if you are doing just bulk compilation anyway. And so it's not a I'm interacting with an IDE kind of tool, at least to date. It could be extended in the future. So the question is then, can we change the rules? What can we do that's actually better than just dropping in and replacing the preprocessor, right? Well, a clear observation is that all of these preprocessing runs are all doing very similar pieces of work, right? They're using the same headers or largely overlapping pieces of headers. They're all groveling around in the file system to look up the same, however many hundreds of headers that have to be looked up through the same search paths or very similar search paths, not necessarily identical, right? Can we do something that's, built to accelerate this? And the answer is, well, we should, because we said that this is a reusable framework and you can use the libraries to do crazy stuff, right? And of course, I'm not going to tell you the answer is no, strangely. And so, giving this talk, I had the inkling that Google people care about DistCC, and so I hacked together a little test that says, well, let's just do the very simple, basic approach of caching file contents for headers and file system lookups for the directory traversal stuff, right? I'm not going to try to do precompiled headers. I'm not going to try to do, caching macro expansions or any of this crazy stuff. Just do the very, very basic stuff, because I only had a couple days, and get this going and see what happens, right? Because I'm curious. And so the idea here is that, say you have a tool like DistCC where you're presented with, preprocess this, you have this big work list of stuff to do. Instead of forking and execing processes to do this, because this is a library-based design, you just link it into your tool, and you just preprocess them one after another, right? And what happens? Well, the answer is that good things happen, right? So the three bars here are, the left bar is GCC 4.2, the middle bar is the Clang number I showed you before, and the third bar is the number with just caching file system related information, right? And what I found is that this is a huge speed increase, and for obvious reasons, right? I mean, you get between a 4.2 times speed up and a 2.6 times speed up, which is 3.3 times average. Unsurprisingly, what ends up happening here is that the system time drops, right? For the biggest ones, Llvm BMK, for example, system time on my Core 2 Duo went from 9.8 seconds to 0.88 seconds, right? So that's a factor of 10 reduction in MMAP, stats, all this kind of stuff, right? You still have a lot of I/O because you're writing out 291 megs of output, right? So it's non-zero. But it scales much better as you add source files to your application, right? Because as you add source files or headers to your application, now the cost per process, it grows basically linear with respect to the amount of source you're throwing at it, not with respect to the source plus times all the headers, number of source files times all the headers, right? So this is a very good thing. Another interesting thing is that in the GCC community, there's been recent work on F directives only, right? Which basically says, well, the preprocessor does a ton of work to keep track of macro expansions, which, looking up the identifier in the big identifier hash table in the sky, for example, takes a lot of time. If you're not tracking pound defines and expanding them, you can go much faster, right? And pound defines almost never really, not never, but almost never are involved with pound include expansion, other things like that. And so you can get by without having to do a lot of the work that the preprocessor has to do that's not related to the file system. Yeah, I know. So, and so I think within the context of GCC, this was a 30% speed up in preprocessing time in some cases, right? Which is huge. Well, if you apply that to this, right, our system time is tiny. So if you reduce the user time by 30%, now you're talking about 6 seconds on the biggest one, or something on that order. Well, if you reduce something that is already 4 times faster by 30% or 33%, now you're talking about a 12x speed up over GCC. That's 12 times more scalability than before, because that's coming straight off the top of user time. That's just work done by the preprocessor you don't have to do anymore. And you let the slave machines dealing with all the grinding stuff do it. Does that make sense? So this is just a hack I threw together. It seems to work really well, but it's not integrated with DistCC, so people can't just take it and use it. If you have tremendous numbers of files laying around that you want to preprocess, it works great, and you can use it right now. Most of us don't. But the point of this is to show you that, with a framework-based, library-based design, you can build interesting, neat stuff in a couple of days, right? And again, this is a couple hundred lines of code, if that. It took more time gathering numbers and figuring out which programs were big and which options you needed to compile them on all this stuff than it did to actually build the code. So that is my talk. So in brief, I discussed Llvm 2.0. Llvm 2.0 came out in May. It has a bunch of new features, and if you're interested in optimizers or backend code gen stuff, definitely check it out. It works really well. We're using it for a lot of different interesting projects. Llvm 2.1 is coming out in September, and so that will bring the next wave of missing features like C++ exceptions, something that a lot of people really want, and optimizer improvements, code gen improvements, and optimizer speedups. Llvm GCC 4.2 will probably be out sometime by the end of the year, and we'll probably maintain 4.0 and 4.2 in parallel for some time, and then eventually 4.0 will fade away in the background. The new C front end is very early on again. It can parse tremendous amounts of C code, and it's really fast, but it doesn't do all the semantic analysis, and code gen is, again, 15% along the way, right? And it's the easy 15%. So fortunately, this is my fourth AST to LLVM translator, so I'm very confident that it will work and have definitely some experience there. But again, it's very early. If anybody is interested or wants to help out or check it out, you can do so. The main LLVM webpage is there, and my really ugly, horrible webpage I threw together in about 10 minutes is available here. So that's about it. Does anybody have any questions? Is the compiler internally serial? What do you mean?
Is it threaded? Is it multi-threaded?
It is not currently multi-threaded. There's different answers to your question, I guess. So the LLVM optimizer itself has this concept of a pass manager. The pass manager is actually built to enable it to be multi-threaded, but nobody has. And so pieces of the optimization pipeline are a function at a time, and so it'd be really easy to enhance that to optimize and code gen a function at a time, for example. That's an easy hack. Nobody's bothered to do it yet. And the front end is not threaded, but the components are built to be threaded, or they're in the, if you want to synchronize outside before you call into it kind of design. And so one of the things we're interested in looking at is incremental parsing on multiple threads to support things like this. Again, it hasn't been done, but I think it can, and we're kind of designing it, assuming that we will at some point. So the answer is no.
So imagine for a moment that somebody wanted to write a Java front end.
Okay.
LLVM. Two questions I have is, one is, what about integration with a garbage collector? Particularly, how do you write a garbage collector that would, be able to look at the stack and all these other things that it needs to be able to trace references?
Can I answer that question before you ask the next one?
Okay.
Okay, so the question is, if I want to write a Java front end for LLVM, how does that interact with the garbage collector, particularly when the garbage collector wants to scan the stack and find all the pointers? The answer is really easy in that LLVM supports that directly. It supports accurate garbage collection. It supports identifying all the pointers on the stack with metadata. So you just do it. Second question.
Question is, with Java, when you import something, you're not importing a header file, you're importing a pre-compiled artifact. Does the intermediate data form have the ability to store information that's only meaningful to the front end? In other words, can you store type information that you could then re-import into your front end if you're importing, let's say, other compiled modules?
So the question is this in the context of C or in Java?
Let's say Java. When you
Okay,
import,
so
when you
yeah.
do a Java import,
So
you
if
import
you're
a .class file, right?
So the question is if you were building a Java front end in Java, when you say import of Java AWT window whatever, you import a class file which contains metadata about the class, doesn't actually contain the class. Do we support this? The answer is no. The reason for that is that C doesn't work that way. We're not trying to support C in the same context, right? If you're to reuse any pieces of our front end, it would be the buffer management, column line number tracking stuff, all of those kinds of pieces. You wouldn't be able to track. You wouldn't be able to reuse the ASTs, the type information, any of that kind of stuff. That said, we do plan on being able to write out the ASTs to disk. We haven't done so yet, but it's a no-brainer. We definitely want to do that. Support PCH, support whole program ASTs, support all these different things. And for that, when we get to it, we definitely will be doing basically a module system similar to the proposals for a module system in C++ that have been talked about at the standards committee meeting. So, yeah.
Is anybody currently using LLVM for any multi-stage programming languages, something cell meta-ML or meta-ML where we've got quoted code where, staged compilation?
So the question is anybody using LLVM for multi-stage programming languages where you have eval and quoted code and things like that? So the answer is I don't know, or I don't know of anybody who is, except that LLVM is heavily used for things like dynamic specialization, runtime code generation. It's used for various scripting languages. So the question isn't really have they, it's could they, and the answer for could they is yes, they could, because all the pieces you can run at static compile time, you can run at runtime. And LLVM was designed that way as a set of libraries. So, yeah. So, yeah.
LLVM have any chance of working as a cross compiler?
The question is, does LLVM have any chance of working as a cross compiler? The answer is yes. In fact, it does so very directly. One of the nice things about the LLVM targets is that they can all function as dynamically loadable plugin things. And by default, for example, LLVM, one of the developer tools is called LLC. LLC is basically all the targets linked together into one executable. So you can take an LLVM bytecode file and say, run through the alpha backend, run through the MIPS backend, run through whatever without having to reconfigure or rebuild any of your stuff. When it comes to LLVM GCC doesn't work that way. LLVM GCC, you have to configure it for the host and target, and it does definitely support that. But you can't just say, okay, I want to target this now. The new front end does support having multiple targets built in, and it supports linking to multiple LLVM targets, and so it does the right thing there. So, yeah.
So it sounded like you parsed the diagonal error in the parser, right?
So the question is, do we parse the expected error markers in the parser? And the answer is no. What we do is the tool that analyzes diagnostics and makes sure diagnostic exists where it's supposed to and doesn't exist where it's not supposed to, does two things. One is when it starts up, it runs the parser, and it installs a special error handler so that it captures and buffers all the diagnostics that come out. So now it knows what the parser actually produces on that input. And after that, it runs the lexer again in keep comments mode, which is the GCC capital C option, right? And so it basically relexes the file. When it relexes the file, it gets all the comments as comment tokens, and it just looks at the comment tokens. And so the parser itself doesn't look at those. This tool, which is used for the test suite, explicitly relexes it, and because it's using the lexer, it doesn't have to deal with figuring out what /star comments mean, all that stuff, but it also gets full column number, line number, all that information for free.
So have you ever had a bug in the lexer causing a test case not to trigger or have a wrong?
So the question is have we ever had a bug in the lexer, at which point you pause, and so the answer is yes, which then got fixed. And the second part was that caused an error not to be caught. And we haven't had that happen yet. So the comment parser has been, it's well established, it doesn't change very much. So it is vectorized and has other cute things in it, but it hasn't been a problem.
Can you translate Java bytecode into LLVM bytecode and vice versa?
So the question is, can you translate Java bytecode into LLVM bytecode and vice versa? The answer is you can translate LLVM bytecode into MSIL bytecode, which is not Java. It is actually more general than Java, and it's actually unsafe MSIL bytecode. You can translate some Java with the GCJ front end for GCC, but nobody's done the work to make it work really right. When you do that, you lose portability of Java. And so the LLVM that comes out of a C front end is necessarily tied to the dialect of C you're compiling for. And so if you compile on an x86 box, or if you compile targeting in an x86 box, the preprocessor strips out everything not related to x86 from the input token stream, right? And so the bytecode file coming out of LLVM, even though LLVM can represent portable programs, is unfortunately tied to x86 or whatever. So given a from scratch written Java front end, you could do the right thing and you could make it work, but nobody's done that. So, yeah, Ian.
What types of inline assembler do you expect to support in the front end? Particularly, do you expect to support that other client, like the Vectorworks?
So the question is what flavor of inline assembler do we expect to support? And the answer is twofold. In LLVM GCC, we currently accept GCC style inline assembly and Code Warrior Microsoft style. In the new front end, I'm sure we will have to do both. So we don't support either really yet. I mean, we parse it, but we don't do anything useful with it. So yeah.
Suppose you wanted to write your Java front end in Java or your Python front end in
Okay.
Python.
Yep.
How easy is it to use a language other than C++ to integrate with the rest of LLVM?
So the question was, say you wanted to write your own Java front end in Java or Python front end in Python. We already talked about Java. Let's talk about Python. So there's this project called PyPy, which is a Python front end written in Python. It actually targets LLVM. It can output LLVM code or C or Java bytecode or something. Their fastest target is with LLVM currently. So there's two ways of doing it. In Python, it's really easy to bind to C class libraries and stuff like that. So I think that's what they're doing. But LLVM has a fully functional, 100% correct text form. And so, for example, we have somebody who wrote a scheme front end by writing a scheme front end in Scheme. He just spits out a big .ll file with all the code at the output, and then just send that through all the existing tools we have. So just turns into run this command, pipe it in this other command, pipe it in this other command, output a .s file, run GCC on it to assemble it, or that kind of thing. So either way, you can either bind to the C++ classes if you want directly, which works really well, or output a text file. And if you bind directly to C++ classes, it works great because you can dump out the text file at any point. So you don't lose anything by doing that.
Is LLVM both a optimizer and a linker? I don't quite understand how to combine multiple compilation needs together.
So the question is LLVM both an optimizer and a linker? And the answer is yes, it is both. It has, so the link time optimization story is actually very different than the GCC one. So LLVM's obviously has an optimizer. It also has a linker that works on its own IR files. And so when you invoke the link time optimizer piece, it links together and it understands visibility, or it understands weak linkage, it understands all that stuff, right? So if you're given two .ll files, you can link them together and it does the right thing. The problem is that LLVM does not want to be a native system linker that knows about archives and knows about the funny rules for when you're supposed to pull a .o file out of an archive. It just doesn't want to know about all the .o file format types and ELF versus Mako versus whatever, PECOF. So it doesn't want to get involved with any of that stuff. Also, the native linker has to do a bunch of work to determine symbol visibility. Oh, if this is visibility hidden, then at this point it gets marked internal. And we could do optimizations, right? Stuff like that. So the way the LLVM link time optimizer works is there's two models. One works similarly to the GCC designed model where it's a standalone tool you invoke. The standalone tool does the linker. It knows some linker options. It tries to make it work. But in practice, it doesn't work very well. People drop it in, and inevitably, they're using some bizarre, weird feature from GNU Linker or something, and it horks, and people don't like it, right? The other option is that we have a liblto dynamic library. And the way the Apple linker works is that when you invoke the linker, just user bin LD on a whole bunch of .o files, the linker just starts popping them open and saying, aha, this is, in the case of Apple, a Mako O file. Great, keep going. Here's a Mako O file. Here's a Mako O file. Here, what the heck is that? I don't know what that is. This looks like an error, right? So on the error path of the linker then, it says, oh, well, I wonder if I have a shared library sitting in this specific spot in the file system. If so, I'll open it. Aha, I have a library. That's great. OK. Do you know what this is? And so it asks it and it says, aha, well, the library, which is an LLVM liblto library, says, yes, I know exactly what that is. I can handle it. Just leave it to me, right? And so the linker keeps going, and it opens all of the .o files. Some are native .o files. Some are LLVM. They might be LLVM and native O files mixed within an archive. It doesn't matter. The linker then asks the shared library for symbol references, symbols that are used, symbols that are defined, stuff like that, so that it can do archive resolution of symbols and pull the right things out of archives and handle all that crap. Sorry to not crap. Linkers are very important, just not my thing. Sorry, Ian. So it does all the hard work, right? When it's done and is decided these are all the .o files I need to process, it then says, okay, liblto, you go optimize, code gen, and handle all the LLVM pieces. And so that runs the LLVM optimizers, it runs the LLVM linker between those .o files, runs the LLVM code generator. The output is a native .o file, which the linker then opens and continues linking with the rest of the stuff. And so the answer there is that all you have to do to use liblto, if your linker supports it, is to just compile with 04. If you compile with 04, and the makefile says run user bin ld, it'll still work, right? No matter what weird, crazy features they're using, which is very nice and very powerful.
So you actually just hand back a .o file.
Yep, we hand back a .o file because the linker already knows how to read them. So, and it's nice if your compiler can directly output a .o file, but if it doesn't, you just invoke the assembler and stuff like that. So, yeah, any other questions? All right. Yeah, thank you.